So hello everyone. In our last class, we were discussing about your basics of control system. So in the last session, we were discussing about transfer function, okay, and poles and zeros, and then we discussed type and order of your transfer function. So in today's session, we are going to talk about your the remaining part of the basics of control, along with your SFG and your block diagram. Okay. So let us then begin today's session. So before that, I wanted to discuss few things regarding your transfer function. Okay. So if we have a system, something like this, so let yt be your output in your time domain and xt be the input in your time domain. And this system is defined by h of t. So we know what y of t is equal to x of t convolution with h of t. Okay, y of t convolution with x of t and h of t convolution. So now if over here we take Laplace transform both sides, so this will be what? Ys is equal to xs into hs, because in time domain if it is convolution, then in transform domain convolution gets converted to your multiplication. So hs becomes what? It is equal to ys by xs. Okay, it becomes ys by xs. So now if you see over here, if suppose xt is your impulse signal, impulse signal, so what is impulse signal? So impulse signal, definition of impulse signal is del t equal to infinite for t equal to 0, and it is equal to 0 for all the other places. And this is not the complete definition of del t. Area under impulse, it is what? It is equal to 1. So this is the complete definition of impulse signal. So if we give xt as impulse, so this will be what? Y of t is equal to del t ht. And if you take Laplace transform of this, so this will be what? Y of s is equal to Laplace transform of del t is 1 dot hs. So you can see what, that if I take basically your inverse Laplace transform, so this will be what? Y of t is equal to h of t. So there is one more definition of transfer function, that is what? Laplace transform of impulse response is what? It is your transfer function. So Laplace transform of impulse response. Now what is this impulse response? See, the output that we get when we give your input as impulse, that is known as your impulse response. Okay, impulse response. So what did I say? Basically that Laplace transform of impulse response is equal to what? It is equal to your transfer function. Now for example, if suppose we have a system, okay, we have a system h of t that is defined as e to the power minus 2t ut. So this is yt, and xt is equal to ut. So find the impulse response of the system. So how do we do that? Impulse response of the system, how do we find it? So look over here. If you solve this, we know what? Transfer function is equal to what? It is equal to Laplace transform of output divided by Laplace transform of input when all the initial values are 0. So output over here, okay, output over here, we actually know what? That it will be equal to e of minus 2t ut exponential, sorry, e to the power minus 2t ut convolution with what? Convolution with your u of t. So if we take your S domain, so this will be what? This will be multiplied with this one. So this is 1 by S plus 2 and this is what? 1 by S. So over here we are going to put S plus 2. So this is your output divided by what is input? Input is ut. So 1 by S. So SS gets cancelled. So you get 1 by S plus 2. So this is HS, transfer function. And we know what? Inverse Laplace transform of your transfer function of a system is your impulse response. Why? Because just now I have told you Laplace transform of impulse response of a system is equal to transfer function. Then if I take inverse Laplace transform, so impulse response is equal to inverse Laplace transform of your transfer function. So if I do that, this will be what? E to the power minus 2t ut. So this is your h of t, which we call it as your impulse response. Okay. So any doubt in this? Okay, fine. So next we have to study what? We have to study your DC gain of the system. So what do we mean by DC gain? So DC gain is the gain of a system at S equal to 0. Okay, basically what? It is the gain of a system at S equal to 0. Now S equal to 0 means what? That your frequency basically over here is 0. So 0 frequency what? DC means 0 frequency means your DC signal. So basically we want to find the gain of a system when 0 frequency signals are applied or when DC signals are applied. Okay. So how do we find the DC gain of a system? So for a type 0 system, I have already discussed the type with you. For a type 0 system, if your transfer function is Gs, which is equal to K Ns by ds like this, then DC gain is equal to limit s tends to 0 g of s. Okay, limit s tends to 0 g of s. For type 1 system, let your transfer function, it looks like K Ns divided by s ds. Okay, so there is one pole at origin in your type 1 system. So for this, your DC gain will be equal to limit s tends to 0. Now if we directly put s equal to 0 over here, DC gain will become infinite. So to avoid that, what we do, we multiply s over here and put gs. When we do that, this s and this s will cancel. So put the value of gs, that will be what? K ns by s ds. Now whatever can be the value of k, ns and ds, so this will all we are going to put 0 and get the value of the constant. Now similarly, if it is your type 2, so for type 2, your transfer function, it will look like, so here also DC gain will be equal to limit s tends to 0 s square gs. Okay, so remember this, whenever there means if your type of the system is 2, 3 or even n, so you need to make a finite quantity. Over here, if we had simply taken s tends to 0 without this s square, then this term would have been infinite. So we need a finite solution over here, finite answer. So due to that, we have multiplied your s square over here. Okay, so is this clear? Any doubt in this? Okay, fine. So next is what we have, sensitivity. Okay, concept of sensitivity. Suppose we have a function a or a variable a, okay, which is actually depending on function b and c. That means what? A is your dependent variable, b is your independent variable, and even c is your independent variable. Okay, so a depends on b and c over here. Okay, so if that is the case, then what do we mean by sensitivity? So with the help of sensitivity, we basically mean that, suppose if I want to find the sensitivity of a with respect to b, that means what? Fractional change in a when we do fractional change in b. Or you can define it like, what is the fractional change in a? Okay, what is the fractional change in a when we do a fractional change in b? That is known as what? That is known as sensitivity of this function a with respect to b. Now I can also define it in terms of partial differentiation, so that will be del a by a divided by del b by b. So this is your what? This is your fractional change in a. I should write it like this. Fractional change in a due to fractional change in b. So that is known as what? That is known as your sensitivity of a with respect to b. Similarly, over here we could have defined sensitivity of a with respect to c. So that will be fractional change in a divided by fractional change in c, which is equal to del a by a divided by del c by c. Okay, so this is what? This is your sensitivity of a with respect to c. Now what we know, transfer function T of s, it is equal to what? Closed loop transfer function, it is equal to g of s divided by 1 plus gs dot hs. Okay, or simply if I remove all this s from here, so I can write T is equal to g divided by 1 plus gh. So what you can see over here, that this transfer function is actually function of forward path gain and feedback path gain over here. Okay, forward path gain and feedback path gain. So now let us try to find sensitivity of this transfer function with respect to g. So that will be what? Del t by t divided by del g by g. So del t by t, if you do partial, means let us write it like this, del t by del g into g by t. Okay, I can write it like this also. So what is del t by del g? Partial differentiation of t with respect to g. So that will be what? 1 plus gh whole square. So 1 plus gh minus this will be what? G h, okay, into g divided by t. So value of t is this g divided by 1 plus gh. So I am taking this 1 plus gh over here. So one of the 1 plus gh gets cancelled. This gh gets cancelled. So what do we get? Even this g and g gets cancelled. So stg, we get it as what? We get it as 1 divided by 1 plus gh. So this is the sensitivity of t with respect to g. Okay, sensitivity of t with respect to g. Now, similarly, if we have to find STH, okay, STH, sensitivity of T with respect to your feedback path gain. So how do we do it? STH, so that will be del T by T divided by del H by H. So that is equal to del T by del H into H by T, where T is equal to what? G divided by 1 plus GH. Okay. So then let us partial differentiate over here. You can see this is the partial differentiation of T with respect to H. So this is very simple. So this will be 1 divided by 1 plus GH whole square. Okay. Here there will be a minus sign along with your GH over here. Okay, this g is due to this g, and this h, it came due to this chain rule, differentiation of this term. So now over here we have h divided by t, so that is g 1 plus gh. So 1 plus gh gets cancelled, and over here this g and g gets cancelled. So this would have been means g square, means I had written h over here, sorry. So this over here, it will come g square, means g into g. So one of the gg will get cancelled. So here it is what? Minus gh divided by 1 plus gh whole square. So this is what? This is your STH, sensitivity of your transfer function with respect to your feedback path gain. Okay, is this clear? Any doubt? Okay, fine. So now let us try to take one example over here. Okay, example. Okay, one thing I want to tell, that this thing 1 plus gh, okay, in this transfer function, this 1 plus gh term, it is known as your desensitivity factor, or also known as your loop gain, or also known as your return difference. Okay, so if you see a question that is being asked, so you need to write 1 plus gh as your desensitivity factor, or your loop gain, or your return difference. Okay, so now let us assume that, okay, so we have one question over here regarding this. So what is the question? Steady state error for a negative unity feedback system is given by ESS is given by alpha by k. The sensitivity in steady state error with respect to alpha and k. Okay, so what is the sensitivity factor with respect to alpha and k? So very quickly you can solve it yourself. So sensitivity of ESS with respect to alpha, so that is equal to Okay, so this will be what? Partial differentiation of this ESS with respect to alpha, so that will be 1 by k into alpha divided by ESS. So ESS is alpha into k. So this k gets cancelled, alpha gets cancelled. So this is 1. So this comes out to be 1. Now what about sensitivity of ESS with respect to k? So directly I am writing now. So this will be dESS by del k into your k by ESS. So if you differentiate this ESS with respect to k, so that will be minus alpha by k square into k divided by ESS. So that is alpha into k. So k gets cancelled with k square, and this alpha gets cancelled. So this is minus 1. So S ESS by k is equal to what? It is equal to your minus 1. Okay, it is equal to your minus 1. So what answer we get? Plus 1 and minus 1. So option B is your answer. Okay. Okay. So now let us try to conclude one very important thing. If suppose we have your open loop system. Okay, open loop system. So if this is g of s, then over here you can see what? That t is equal to what? T of s transfer function. Transfer function is equal to cs by rs, that is equal to g of s. So you can even write t is equal to g. Now if I want to find, basically here t is function of g. So if you want to find stg, so that will be what? Del t by del g into g by t. So del t by del g, so that will be equal to 1, and g by t, as g is equal to t, so even this will be 1. So stg is equal to 1. Okay. Now if suppose there is a perturbation of 10% in d, means what? Perturbation means what? There is your fractional change of 10% in your del g, means del g by g. So then how much is the fractional change in the transfer function? So we know what? STG is equal to 1, and this is equal to del t by t divided by del g by g is equal to 1. So this value is given to us as 10%. So del t by t is equal to what? It is equal to your 10% over here. Okay. So if there is a fractional change of 10% in the forward path, then your transfer function will also have what? It will have 10% change. Overall transfer function will also have 10% variation. Okay. Now suppose we take the same example in case of your closed loop system. So if we take your closed loop system, now let us assume that parameter variation in G is what? It is again 10%. Okay. You can even assume minus 10%, but I am assuming plus 10%. Okay. So now what is the overall means what is the overall change in your forward path? So how do we calculate? T is equal to G divided by 1 plus GH, and we know what STG is given by what? It is given by G divided by 1 plus GH. So here actually we need the value of G and H to calculate what? To calculate this STG. So how do we do that? Let us assume that G is equal to 100 and H is equal to 10. So if that is the case, then this will be 100 divided by 1 plus 10 into 100. So this is equal to what? This is equal to approximately equal to 100 divided by 1000. Okay, approximately. So you can write this to be as 0.1. And we know what means STG is equal to 0.1. Just now we have calculated. So STG is what? Del T by T del G by G. So this is equal to 0.1, and del G by G is 10%. So that means what? Del T by T is equal to 1%. So you can see, if you disturb the forward path by your 10%, your overall transfer function gets disturbed by only 1%. Okay, by 1% only. Now for the same case, assume that we are disturbing the feedback path by 10%. Now what happens? So we know what? STH is equal to minus GH divided by 1 plus GH. So this will be minus 100 into 10 divided by 1 plus 100 into 10. So this will be approximately equal to minus 1. Let us assume. So STH means what? Del T by T divided by del H by H. So that comes out to be minus 1, which implies this value is 10%. So del T by T comes out to be what? It comes out to be your minus 10%. So that means what? If we disturb the feedback path by 10%, your overall transfer function, it also gets disturbed by your factor of 10% in magnitude. So over here we are getting minus 10%. Okay. So remember this, that your variation is very less. If you want to write one statement, variation in overall transfer function due to variation in forward path is less as compared to variation in feedback path. Okay, so such kind of statements will be asked in your PSU exams, that what is the variation of your transfer function when you change by this much in your forward path, or when there is a change in your feedback path. So you are going to calculate it with the help of your this sensitivity of a transfer function. So one more statement also you can write, that your closed loop system is less sensitive. So I will write it, closed loop system is less sensitive with respect to perturbations, or you can even write disturbance in bracket, with respect to perturbations in forward path, and is highly sensitive with respect to perturbation in feedback path. Okay, so this is one very important result that we should know. Okay, so next is what we have: significance of poles. Okay, significance of poles. So the definition of poles I have actually discussed with you in your last class, that what is poles, what is zeros, all the things we have actually discussed in your last class. So what do we mean by poles? So poles are basically all those frequencies of your transfer function, or all the values of s in the transfer function where your magnitude of the transfer function goes to infinite. Okay, or basically whenever the denominator, it is basically the roots of denominator of your transfer function. Okay, so what are the significances of poles? Okay, so that we need to see. So poles basically, first of all, poles describe your stability of the system. So right, poles describe the stability of the system. Okay, so one by one we will discuss all the points later on. First let me write. So poles describe the stability of the system. Then poles basically do what? So poles, with the help of poles only, in your next to next chapter, that is your time response, we are going to calculate maximum peak overshoot, settling time, and all the quantities. So I am going to write poles describe the time domain parameters like your maximum peak overshoot, settling time, okay, etc. Even delay time, peak time. So all those things we will see later on, but at the moment just note over here. Okay, poles describe the time domain parameter of system. Third is what? Poles describe the time constant. So this we are going to discuss just now. What is time constant? Poles describe the time constant of system. Okay, time constant of the system. Poles describe the frequency of oscillation of system. Okay, fifth point, poles describe the type and order of system. So we have already discussed this point, that what is type and order of the system. So we are not going to discuss on this point. Now what is the first point that I have written? That your poles describe the stability of your system. How? So first point, let us take. Poles describe stability. Okay, so we should know that in control system, okay, in control system, basically all the systems that we take, they are what? They are your causal system. Okay, causal system. So what do we mean by causal system? That h of t is equal to 0 for t less than 0, and h of t not equal to 0 for t greater than equal to 0. So this is what? This is your causal systems. Okay, so if means, another way of telling is that in your control system, basically your output, it depends only on your past output or your present input. It doesn't depends on your future inputs. So such kind of system are known as causal system. Okay, where your output doesn't depends on your future inputs. So in control system, all the systems are basically causal, because if it is a non-causal system, you cannot write transfer function. Okay, so causal system. So for causal system, the condition of stability is that if all poles lie on the, so this is your S plane. This is sigma, this is j omega, this is real part of S, this is imaginary part of S. So S is equal to what? Sigma plus j omega. If all the poles lie on the left hand side of S plane, okay, then your system is stable. Left side means what? In this region, complete this region. Next is what? If all poles lie on the imaginary axis, imaginary axis means what? On this axis. Okay, so one thing I forgot to tell you, poles are represented with cross and zeros are represented like this. Okay, so if all the poles lie on your imaginary axis, then your system is marginal stable. And if your poles are in your right hand side of S plane, then system is what? System is unstable. Okay, system is what? System is your unstable. Okay, system is unstable system. And one more thing, if you have repeated poles on imaginary axis, that means what? You have one set of pole over here, let us assume. So this is J1, this is minus J1. Always remember, poles exist in conjugate pairs. And if there is one more set of pole over here only, then such kind of system is also unstable. Okay, so repeated poles on imaginary axis are what? It is your unstable. So this is what? This is your first point. Next point, so we have completed this one. This point we are going to see in your third chapter. Now what is this? Poles describe the time constant of the system. So third point, time constant. Okay, so what is this time constant? So first write the definition of time constant. Time constant is defined as the reciprocal of magnitude of negative real root. So what I said, time constant, also written as tau, is defined as reciprocal of magnitude of negative real root. Okay, or roots, whatever you want to say. Now what do we mean by this? Suppose if we have a transfer function Ts that is equal to 1 divided by s plus 10. So if I draw the pole zero plot for this, so this will look like this. Okay, so if I want to find the impulse response of this, so this will be what? Means I should have written it as h of s, yeah, g of s. So let me denote it by h of s. So h of t will be what? If you take inverse Laplace, this will be e to the power minus 10t ut. So basically, what is the time constant over here? So time constant is defined as reciprocal. So reciprocal of magnitude of negative real root. So this is your negative real root. So first you need to take reciprocal of this, then take magnitude. So this is what 1 by 10 second is the time constant of the system. Now what is this physical significance of this time constant? So let us try to draw the graph for e to the power minus 10t ut. So it looks something like this. Okay, it looks something like this. So its initial value is what? It is equal to 1. Now basically time constant is that value of time where your system has decayed by 36.8% of your initial value. Okay, 36.8% of your initial value. Now when is that going to happen? If you put t equal to 1 by 10 in this equation, so that will be e to the power minus 1 u of 1 by 10. So u of 1 by 10, that will be 1. So e inverse, what is that equal to? That is equal to 0.368. So what did I say? Time constant is basically that value of time in an exponential signal when it decays by 36.8% of the initial value. So that is known as what? That is known as your time constant. Okay. So you can see basically time constant comes out to be 0.1 second or 1 by 10 seconds over here. Okay. So, okay. Let me ask you, what is the time constant for this system? What is the time constant of this system? So here you can see there are basically two poles. Okay, there are two poles over here. So if I draw the pole zero plot, so one of the pole is at s equal to minus 1, another pole is at s equal to minus 2. So for this, time constant will be equal to 1 divided by minus 1 magnitude, and for this your time constant will be what? It will be minus 1 divided by 2 magnitude. So this will be half second and this will be 1 second. And even if you calculate h of t, so if you take partial fraction over here, so h of s is equal to 1 by s plus 1 minus 1 by s plus 2. So if you take now inverse Laplace transform, so this will be, so when is this decaying exponential going? 36.8% of its initial value. So that will be at t equal to 1 second. And over here you can see at t equal to half second, this is going to be at 36.8% of its initial value. So you can see from this concept also we are getting the same answer that I have told you. Okay. So this is what? This is your basically time constant of your system. Okay. So now let me ask you, what is the time constant for this system? So what will be the time constant for this system? So over here you can see the poles will be what? So if you solve this, you will get S equal to minus half plus minus J root 3 by 2. So one of the poles will be over here, another will be over here. And always remember that poles exist in your complex conjugate pair. So minus half plus J root 3 by 2, and this is minus J root 3 by 2. So over here, the time constant will be what? Time constant is equal to your reciprocal of the negative real root. Okay, magnitude, reciprocal of magnitude of negative real root. So that will be 1 divided by minus half, because this is your real part of this pole. So S1 is equal to what? There are two poles. So S1 will be minus half plus J root 3 by 2, and S2 will be what? It will be minus half minus J root 3 by 2. So this is your negative real part. So reciprocal of that, and you take magnitude. So this comes out to be 2 seconds. Now can you guys do one thing? Can you take the inverse Laplace transform of this transfer function? Inverse Laplace transform. See if this is okay or not. Look over here. Is this okay? So this will be 1 by 4 plus 3 by 4. And this 2 will get cancelled. Okay. So same thing you will be getting over here. So this I can write as 10 divided by S plus half whole square plus root 3 by 2 whole square. So what I can do, I can multiply with root 3 by 2 and divide it by root 3 by 2. Now we know what? Sine omega naught t ut has Laplace transform s square plus omega naught square e to the power minus 80 sine omega naught t ut has Laplace transform what? Sorry. So this will be omega naught over here. So this will be omega naught divided by s plus a whole square plus omega naught square. And you can see this is in the same form over here. Okay. This much. So this is in the same form like this. So what I can write, this is actually equal to what? If I take inverse Laplace transform, so this will be 10 divided by root 3 by 2. So let me take this over here. So 20 by root 3, and this will be e to the power minus half t sine root 3 by 2t ut. Okay, this will be the expression for what? H of t. Now if you plot this h of t, it will look like, so this will look like this. So basically at t equal to 2 seconds, okay, t equal to 2 second, initial value over here it is 0, but for this exponential, what it is, for this exponential it will be 20 by root 3. Okay, 20 by root 3. So at t equal to 2 second, it will be 36.8% of this 20 by root 3. So time constant means this. And over here you can see that basically our poles where S1 is equal to minus half plus j root 3 by 2, and S2 is equal to minus half minus j root 3 by 2. So this complex part or the imaginary part of your poles, they basically describe what? They describe the damped frequency of oscillation. Damped frequency of oscillations, you can see. So I have written one point, you can see in point number 3 or point number 4, I guess. Okay, that poles describe the frequency of oscillations of the system. So you can see that basically your imaginary part of the poles describe what? It describes your frequency of oscillation, whereas your real part, it describes the time constant of your system. So is this clear? Any doubt in this? So over here, time constant is equal to 2 seconds and frequency of oscillation equal to what? It is equal to root 3 by 2 or 0.866 radian per second. Okay, so this is the answer to your question. Okay, so all the points we have discussed over here. Okay, all the points we have discussed one by one. So this point we are going to see in your chapter number 3. Okay. Next is what? Next is your initial value theorem. Suppose if our transfer means impulse response is h of t and its Laplace transform is your transfer function. Okay, so that is h of s. So if I put t equal to 0, I will be getting the initial value of this impulse response at t equal to 0. Now if suppose if I directly want to find h of 0 using this using this transfer function, how can I do it? We can do it with the help of initial value theorem. So that will be equal to limit s tends to infinite s h of s. So this is your initial value theorem. Okay, this is your initial value theorem. Now one thing to note over here, okay, let me ask you guys only. So when is initial value theorem valid and when is it invalid? Can you tell me? So when is initial value theorem valid and when it is invalid? See, initial value theorem, it is valid. So note point. Initial value theorem is valid for both stable and unstable signal, because both stable and unstable signal, it will have initial value. Like one of the example of unstable signal is what? E to the power 2t ut. So this is your what? This is your unstable signal because its graph look like this. Okay, so this is unstable signal, but still it has initial value of 1. But initial value theorem is invalid for what? It is invalid for our what to say? So it is invalid means I forgot the term. Yes, improper transfer function. Improper transfer function. So now what do we mean by this improper transfer function? When order of numerator is greater than or equal to order of denominator, then it is known as your improper transfer function. For example, if suppose h of s is equal to s square plus s plus 2 divided by s. So what is the order of numerator? Order of numerator is 2. Order of denominator is 1. Okay. So here if you take partial difference, means sorry, if you take your inverse Laplace transform, so this will be what? S plus 1 plus 2 by S. So for this, remember, if del t has Laplace transform of 1, so d by dt, del t will have Laplace transform what? It will be S. Okay, S, this will be S. So this will be del dash t, 1 will be del t, plus 2 by S will be 2 ut. So at t equal to 0, basically del t is what? It is infinite at t equal to 0. So that is why for your improper transfer function, initial value theorem does not exist. Why? Because you can see that we will be getting infinite. But if you put this formula, you might get one finite value. Like if you put limit s tends to infinite, s into s square plus 2s plus 2 divided by s. So over here you are seeing what? SS gets cancelled. So over here also you are getting infinite. Okay. So this theorem, it will not hold true when you have what? When you have your initial, means when it is improper transfer function. So here you are getting infinite. But if suppose your transfer function was like this, hs is equal to s plus 2 by s. So if you take the inverse Laplace transform, so that will be 1 divided by 2 by s. Okay, it will look like this. So this is what? Del t plus 2 ut. Okay, so again you can see if you put t equal to 0, this will be infinite. And if you put initial value theorem over here, so that will be what? Limit s tends to infinite, s into s plus 2 by s. So this gets cancelled. So you can see s plus 2, again you are getting infinite. So initial value theorem is invalid for your improper transfer function. Now next is what? Next we have is your final value theorem. So again, if h of t has Laplace transform h of s, okay, h of t has Laplace transform h of s. Basically this h of t is what? It is impulse response. So Laplace transform of impulse response is your transfer function. Now with the help of this, if we put t tends to infinite, we get the final value of your impulse response. Now if we want to directly find it from your transfer domain, so what we do? We put limit s tends to 0 s hs. So this is what? This is your final value theorem. See, we are not deriving any one of the following because derivation is not required in your PSU exams. Okay, derivation is not required. So over here you can see this we get. So again one note point. Note point is that final value theorem is not valid for unstable system. Okay, it is not valid for unstable system. Like if h of s is equal to 1 by s minus 2. So we know what? If we take your inverse Laplace transform, so this will be e to the power 2t ut. If you put t equal to infinite, this will be infinite. But if you apply final value theorem, that will be what? Limit s tends to 0 s into 1 by s minus 2. So you can see if you put s equal to 0, so this will come out to be 0. So this is invalid result. So that is why we never apply final value theorem where? When your system is unstable. So always whenever you get questions of final value theorem, please just check once whether your poles, all the poles, if they are lying in your left hand side of your S-plane. Now if suppose hs is equal to 1 by s square plus 2. Okay, so this will be what? This will be actually if we take inverse Laplace transform, so okay, let me take just one over here, so that will be simple. So this will be sine t ut. Now if you put t tends to infinite, basically we don't know what will be the exact value. We only know that the value will lie between your -1 and +1, because that is the range of sine function. So sine function, it will lie between -1 and 1 for t tending to minus infinite to plus infinite. But the definite value we cannot say for your h of s. Okay, we cannot say that definite value. So that is why if we apply final value theorem over here, so look what we get. So this will be s into 1 by s square plus 1. So this comes out again to be 0. So this is also invalid. Okay. So never apply final value theorem to unstable system. Unstable means totally unstable as well as your marginal stable. So add marginal stable also over here, so that basically you remember that unstable means what? Completely unstable as well as your marginal stable system. We never apply final value theorem. So now let us talk about what? Talk about stability analysis in positive and negative feedback system. Okay. So if suppose we have a system, open loop system like this. So if we draw the pole zero plot, so you can see pole will be at -10. Okay, this will be at -10. So if you see over here, basically, so this is one stable system. Now if we take the same open loop system and close it using negative feedback, where your feedback path gain is 5, let us assume. So the same system is over here. So this is a negative feedback system. So over here I have taken 5. So then transfer function is equal to what? G divided by 1 plus gh. Okay. So that is 1 by s plus 10 divided by 1 plus 5 divided by s plus 10. So this will be equal to what? This will be equal to 1 divided by s plus 15. So if you draw the pole zero plot, you can see one of the pole, it is at s equal to -15. So if a system, if there are two systems, in one of the system, you can see pole is what? Pole is at -10, and at this system, you can see pole is at -15. So out of these two systems, which do you think will be more stable? So more stable will be the system whose poles lie in the farthest from your origin, means whose pole lie in the farthest from your origin, or the pole that has, means the system that has pole in the farthest left in the S plane, that is your most stable system. Why so? Because if you write your impulse response for this one, So C of t will be equal to what, as Rs equal to del t. So that will be equal to e to the power minus 10t ut, and over here it will be what, it will be equal to e to the power minus 15t u of t. So out of this two, which do you think will decay the fastest, or whose response will be the fastest? So this system will reach 0.368 at 1 by 10 second, whereas this system is going to reach 0.368 at 1 by 15 seconds. So you can see this is reaching this value at a less time compared to this one. So that is why this is more stable. Okay. So a negative feedback system is more stable compared to your open loop system. And already I have told you that negative feedback system increases what? Increases the stability of the system. But if you calculate the DC gain over here, so DC gain will be equal to what? It will be equal to 1 by 10. Whereas DC gain over here, it will be what? You can see 1 by s plus 15. So that will be 1 by 15, as this is type 0 system. So you can see stability is increasing, but gain of the system is decreasing. So negative feedback system is increasing the stability at the cost of decreasing the gain of the system. So remember this point. This might be asked in your theoretical kind of questions. Okay. Now if suppose the same system, instead of doing negative feedback over here, let us do what? Let us take positive feedback. So if we take positive feedback, okay, so positive feedback will be what? You can see over here. So Cs by Rs is equal to 1 by s plus 10 divided by 1 plus, means sorry, 1 minus 5 by s plus 10. Okay. So this will be what? 1 divided by s plus 5. So now if you again draw the pole 0 plot, okay, so this will be what? Over here s equal to minus 5. So here you can see the stability is decreasing as compared to your open loop system. Why? Because if you write, so that will be e to the power minus 5t ut, and this will decay to 0.368 at 1 by 5 second. So you can see basically your stability is decreasing over here. Okay, stability is decreasing because your pole is moving towards the origin. Okay, and over here this was your open loop, s equal to minus 10, and closed loop was somewhere over here, s equal to minus 15. Sorry, this is your negative feedback closed loop, this is your positive feedback closed loop. So stability is the least in your positive feedback, and we also know that positive feedback system basically decreases the stability of your system. But you can see if you calculate the DC gain over here, so DC gain is equal to 1 by 5. So stability is decreasing, but your gain of the system is increasing. So there is a trade-off between stability and gain of your system. Okay. So as your settling time, if you want to say, you can even say, means this I will be telling in your third chapter, as your settling time decreases, your stability increases. Okay, stability increases. So there is a inverse relationship between settling time as well as your stability. Okay, so next is what? Next is the concept of your dominant pole system. So what is this dominant pole system? dominant pole system, basically we use this concept of dominant pole to actually do what? To actually your approximate the system. So we have higher order system. So up till now we have taken first order and second order system. So sometimes what happens, we even get third order system. Okay, so third order system or fourth order system, basically we can do what? We can approximate the systems. Okay, we can approximate the system. So how do we do that? With the help of your dominant pole. So look very carefully, what is this dominant pole concept? So first let us write few points over here. So dominant pole concept is used for approximating higher order transfer function to lower order transfer function. Okay. So in dominant pole, there is one concept, very important. So DC gain before approximation should be equal to DC gain after approximation. Okay, so DC gain before approximation is equal to DC gain after approximation. Okay, so now let us understand this concept of dominant pole with the help of an example. So assume if we have a system that is 100, or simple, let us keep it 1 divided by s plus 1, s plus 10. So this is a second order system. Okay, this is a second order system. Now if I draw the pole zero plot, so one of the pole is over here at -1, another pole is at -10. So the pole that is nearest to the origin, that is known as your significant pole, and the pole that is farthest from the origin, it is known as your insignificant pole. Okay, it is known as your insignificant pole. So now basically for your approximation to take place, the condition is that distance between insignificant pole and significant pole, it should be greater than equal to 5. So here if you see, so that is what, -10 by -1, if you take mod, so this is actually greater than 5, so you can do the approximation. So what is DC gain over here? So DC gain, if you see, so as this is type 0, so limit s tends to 0, 1 by s plus 1, s plus 10, so this will be 1 by 10. Okay, so this will be what? This will be 1 by 10. So DC gain before approximation is 1 by 10. Now basically what we do, we can remove this insignificant pole. Why? Because here it is second order and we want to do approximation. So approximation of second order can be your first order system. So basically we will remove this pole. So HS is what then? So this will become, so this is your approximated transfer function. So this will be 1 by s plus 1. Now if you see the DC gain of this, so that comes out to be 1. But I told you what? That DC gain before approximation and after approximation, it should remain the same. So H tilde S, basically this is the approximated version of this transfer function. So this will be equal to 1 by 10 s plus 1. Okay, so this will be 1 by 10 s plus 1. So this is what? This is your approximated transfer function. Now if in case your transfer function was like this, so now here you can see, if you draw the pole 0 plot, so this is -1, this is -3, so this is your significant pole, this is your insignificant pole. So the distance between your insignificant pole and significant pole, okay, so this will be what? This is equal to -3 by -1. So that is actually not greater than equal to 5. So here you cannot approximate this. Okay, you cannot approximate this second order system to your first order system. Remember this. Okay, so here you cannot do approximation. So this is basically what? This is the concept of dominant pole that you need to remember. Okay, fine. So now we have few questions over here. So this is the first question. I want all of you to try this. Okay, so try this question. So I will give you like 1 minute to solve over here. So answers, anyone? Okay. So now look, I will solve. A plant has open loop transfer function GPS is equal to 20 divided by s plus zero point 0.1, s plus 2, s plus 100. The approximate model obtained by retaining only one of the above pole, which is closest to the frequency response of the original transfer function at low frequency. Okay, so basically you need to do what? You need to do here dominant pole concept over here, or approximate this third order system to a first order model. So you can see GPS is equal to what? It is equal to 20 divided by s plus zero point 0.1, s plus 2, s plus 100. So this will be equal to what? Means if you calculate the DC gain, so DC gain over here will be equal to limit s tends to 0. So this will be 20, means GPS. So this will be equal to 20 divided by 0.1 into 2 by 100. So 0, 0 cancel. So you can see 1. So 1 is the DC gain. And what are the poles present over here? So you can see one of the pole is at -0.1, another is at -2, another is at -100. So what is the distance between these two? You can see -2 by zero point 0.1 minus zero point 0.1, so that is greater than equal to 5. Even -100 by minus zero point 0.1, so that is also very greater than 5. So we can basically neglect this two pole, and our approximated transfer function, it is equal to, let us take only this one, so that will be what, 20 divided by s point 1. But when we do this, you can see over here that what we are getting, that our DC gain becomes what, DC gain becomes 200. So what we can do, we can divide it by 200, so that DC gain becomes 1. So now if we do this, so this gets cancelled, and over here this will be 10. So your approximated transfer function is 0.1 s plus 0.1. That is what, option A is your correct answer. So next question is this, very quickly calculate this one. So you can see over here, the unit impulse response of a unity feedback system is given by this, the open loop transfer function. Very simple. So unit impulse response. So this is what, this is unit impulse response. So I need to take what? You need to take your open loop transfer function. So that is simply what? Laplace transform of impulse response is what? It is equal to your open loop transfer function over here, because this is the impulse response of a, okay, so the unit impulse response of a unity feedback. So look very carefully, this is unity feedback control system. So this will give you the transfer function of a unity feedback system. So that is what, minus t e to the power minus t plus 2 e to the power minus t. So for this one it will be what, minus 1 s plus 1 whole square, and this will be 2 divided by s plus 1 whole square. So this will be s plus 1 whole square over here. Sorry. So this will be what? Minus 1 plus 2 s plus 1. So this will be 2s plus 1 divided by s plus 1 whole square. Now if without proper reading the question, if you have to mark, then option A you will going to be mark, and that is the wrong answer. Why? because they have asked the open loop transfer function. This is the closed loop transfer function for a negative unity feedback. So I have told in the last class, if nothing is mentioned that whether it is positive or negative unity feedback, you always need to consider negative unity. Negative unity feedback you need to consider. Okay. So over here, this will be g divided by 1 plus g is equal to 2s plus 1 divided by s plus 1 whole square. Okay. So if you solve this, so g divided by 1 plus g minus g, so this will be 2s plus 1 divided by s square plus 2s plus 1. I have expanded this and subtracting the numerator. So this means gg will get cancelled. So this implies g equal to 2s plus 1 divided by s square. So which option? Option B is your correct answer. Okay, solve this question. So this was asked in ISRO 2018 for electrical branch. Okay, so if we solve over here, what is the impulse response for the system indicated below? So impulse response you need to find. So CS by RS. Okay, so that will be equal to 1 by TS. Okay, so if you multiply with TS, this will be 1 divided by 1 plus ST, and RS will be equal to 1 over here. Why? Because it is given impulse response. So RT is equal to del T. So RS will be equal to 1. Okay, RS will be equal to 1. So okay, if we solve this over here, so CS comes out to be, means if you take 1 by T common, so this will be S plus 1 by T. So C of T will be equal to 1 by T e to the power minus T by capital T ut. So which option do we see over here? Option A is your correct option for this question. Very simple. So the next question is this one. Quickly solve this one. So it is given the open loop DC gain of a unity negative feedback with closed loop transfer function. So this is a closed loop transfer function. Okay, so without reading the question, if you calculate the DC gain, then DC gain will be 4 by 13 over here. But 4 by 13, it is for closed loop transfer function, your DC gain. But here it is asked DC gain of your negative feedback system. Okay, negative feedback system for open loop. Okay, so first we need to calculate the open loop transfer function. So again, the same thing. So this will be s plus 4 divided by s square plus 7s plus 13 minus s minus 4. So this will be s plus 4 divided by s square plus 6s plus 9. So this will be what if you calculate DC gain? So this comes out to be 4 by 9. So 4 by 9, option B is your correct answer. Now calculate this one quickly. So over here it is given the system GS is equal to 0.8 s square plus s minus 2 is subjected to step input. The system output y of t as t tends to infinite is. So GS is what? It is the system. So CS by RS is equal to what? It is equal to 0.8 s square plus s minus 2. Okay. So RS is equal to what? It is subjected to step input, means over here it is actually not CS. I should be writing YS by RS, where Y is your output, Laplace transform of output, and RS is the Laplace transform of your input. Okay. So RS is your step input, so that is 1 by S. So Y of S is equal to 0.8 by S square plus s minus 2. Okay, so what we need to find over here? Y of infinite. So we can apply what? Initial value theorem. Sy of s, so that is equal to s into zero point 0.8 divided by s square, sorry, s square plus s minus 2. Okay, so this if you solve, so this will be what? This will be coming out to be minus 0.4, option C. But this is wrong. Why? Because this transfer function is unstable. Calculate the poles over here. Calculate the poles. So S will be equal to what? It will be equal to means S square plus S minus 2. So minus 1 plus minus 1 plus 4AC. So that will be 4 into 2, 8 by 2. So this will be minus 1 plus minus 3. Okay, so directly also I could have done. Is this is minus 2 plus 1. Okay. So directly also. So one of the poles, you can see this is in the right hand part of S plane, this S equal to 1. So this is unstable. So that is why unbounded you are going to mark. Okay. Option D will be your correct answer. So whenever in this final value theorem kind of question, wherever you are applying, if you see one of the option as unbounded or does not exist, please check whether the transfer function is stable or not. If all the values are numerical values like zero point 0.8, zero point 0.4, minus 0.4, 0.6, so then there is no actually option given for this infinite to happen. That means your transfer function is stable. But if any one of the option is unbounded or does not exist, then you need to check for your stability of the transfer function. Okay, is that clear everyone? Okay, so solve this question very quickly, then we will go to SFG and block diagram. So solve this question. Okay, so what is given over here? A feedback control system with high gain K is shown in the figure. Then the closed loop transfer function is sensitive to perturbations in GS and HS, sensitive to perturbations in GS, but not to perturbations in HS, sensitive to perturbation in HS, but not to perturbation in GS, insensitive to perturbation in GS and HS. So first, let us calculate CS by RS. So that will be equal to what? That will be equal to KGS divided by 1 plus KGS. Okay, KGS divided by 1 plus KGS. So that will be equal to what? So I can even divide the numerator and denominator by 1 plus KGS. So this will be equal to 1 divided by 1, means over here HS will be also present. So KGS plus HS. So this is what? This is your TS. So as it is given high gain K, so this value will be approximately equal to 0. So TS is equal to what? It is approximately equal to 1 by HS. So you can see it is kind of independent of GS. So even if I disturb GS, it won't be affecting TS that much. So if I disturb HS, there will be a disturbance in TS. So which option do you see? Sensitive to perturbations in HS, but not to perturbations in GS. Option C is your correct option. Okay, option C is your correct answer. Okay. Okay. So now let us talk about what? Signal flow graph and block diagram representation. So in the last chapter, we have actually discussed about what? We have discussed about all the how to basically see the basics of your control system. Like we have studied your poles, zeros, transfer function, how to represent transfer function, all those things we have seen. But now let us see how to represent a system using your block diagram and signal flow graph. So basically this block diagram, it is used to do what? It is used to determine the overall transfer function of the system. And it is what? It is your pictorial representation of your system. Okay. And also for the analysis in your control system, or to be very precise, in your classical control system, we use what? We use your block diagram. Okay. So let us see one by one how to actually reduce your block diagram, because block diagram can be very big. So we need to actually reduce it to get your transfer function of the system. So there are few rules actually for your what? For your reduction of block diagram. So first is what? How to represent closed loop system. So here you can see I haven't actually given any of the arrow. So if this is your positive and negative feedback system, then we can reduce it to CS by RS is equal to G of S divided by 1 minus plus G of S dot H of S. Okay. So if it is your positive feedback, then negative will come over here. If it is negative feedback, positive will come over here. Now if in this HS equal to 1, that means what? Unity feedback system. Then we can reduce this whole diagram, block diagram, to CS by RS is equal to GS divided by 1 minus plus GS HS. Okay, we can do this. Now next is what? Block connected in your series. Okay, if we have blocks connected in series, or you can even say blocks connected in cascade, then simply remember over here YS by RS, it will be equal to what? Product of gain of these two blocks. So that will be G1S dot G2S. Okay, G1S dot G2S. When blocks are connected in parallel, so here also I haven't given any sign. So if this is plus minus, this is also plus minus, then these are blocks connected in parallel. So you can write what? CS is equal to C. From here, RS is being given to both of the blocks. So over here we will be getting what? Plus minus G1s into Rs, and over here what we will get? We will get plus minus G2s into Rs. So we can write it like this: plus minus G1s. Okay, depending on whatever is the sign of G1s and G2s, we can write it like this. Okay, if suppose if I take a particular example over here, so over here it is plus, over here it is minus. So CS will be equal to what? It will be equal to Rs into G1s minus Rs into G2s. So this will be equal to what? R of S common, G1s minus G2s. Okay. So simply we are subtracting according to the sign given in the comparator. Now next is what? Shifting of takeoff point before a block. So how do we do this? Actually, see, students, they'll try to remember or memorize. Okay, but you should never memorize. Only thing you should remember that before manipulation and after manipulation, output of none of your branch should change. Okay, before manipulation and after manipulation. So look over here, that this is your takeoff point, this is C. So C is equal to what? You can see R is supplied over here, so this is input, so this is Rg, and from here also this is Rg. So if I take this takeoff point behind this block, then also your output should be Rg. So look, if I remove this from here and now take it over here, so previously your input was Rg, but now you can see what? That it is simply R. Okay, it is simply R. But I told you what? Before manipulation and after manipulation, what should happen? Output of all the basically takeoff point or any point, it should remain the same. So what I should do over here? I should introduce one block that should have gain G. So now you can see after shifting this takeoff point behind this block, my output of this takeoff point is what? It is again same before manipulation, so Rg. So this is why students, they remember that whenever a takeoff point goes behind a block, we multiply it with the gain of the block that behind which your takeoff point has been taken to. So next is what? Shifting of takeoff point after a block. So again we are going to follow the same thing. So over here before manipulation it is R. So after manipulation also it should remain R only. So look over here. If we take this point over here, so now you can see basically this C is equal to Rg, and this point has also become Rg. Previously it was R, now it is Rg. So there is a change. So we need to manipulate it. So what we should do over here? We should add one block such that the gain of the block is what? It is equal to 1 by G. If this happens, then once again what will happen? You can see from here we are getting Rg as input, and when this Rg is getting multiplied with 1 by G, we are simply getting R, which is actually equal to what? Actually equal to before manipulation. So that is why usually students, they memorize that when a takeoff point that goes before a block, okay, So we need to multiply with the reciprocal of the gain of the block before which the takeoff point is going. Okay. So this is the logical way or the mathematical way with which we can calculate. Now next is what? Shifting of an adder before a block. So this is very important. You can see over here that before means this is the initial case. So over here your output is what? It is means first let me calculate over here. So that will be R1G. So let us use some different color. So this will be R1G1 over here. So that will be R1G1 plus R2. And over here this will be what? This will be equal to G2 R1G1 plus R2. Now after taking this over here, nothing should change. Okay. So look what to do. See, we are taking this block over here. Okay. So this is R2. This is R1. So erase everything from here. Okay. Not required. So now see what is your output over here. Okay. According to that, we will do manipulation. So over here, we can see it will be R1 plus R2. Over here, it will be G1 R1 plus R2. And over here, it will be G1 G2 R1 plus R2. So in the last case, if you solve it once more, so this will be G1 G2 R1 plus G2 R2. This time what you get? You get G1 G2 R1 plus G1 G2 R2. So over here you can see this G1 is not required. This is same as before, but here this G1 is not required. So what should we do? Simply, if you add one block over here instead of R2, you add one block such that it is what? It is 1 by G1. And now if you give R2 as input to this block, now look what you get. You will be getting over here R1 plus R2 by G1. Over here it will be G1 plus R2 by G1. Over here again R2 by G1. So this G1 will be getting cancelled over here. So you will be again getting the same result. So no need to memorize. Okay, no need to memorize. Whenever your comparator it comes behind a block, you simply need to do what? You need to multiply it with the inverse or the reciprocal of the gain of the block behind which the comparator or adder it is going. Now next is similarly what? If your adder means adder or comparator, it goes ahead of a block. So once again with the same logic you calculate output at each place. So this will be R1 G1 over here. At this point it will be R2 plus R1 G1. Over here it will be what? C is equal to G2 R2 plus R1 G1. So solve it once more. This will be G2 R2 plus G1 G2 R1. Okay. Okay, fine. So now if we take this block ahead, so what will happen? So let me draw it very quickly. So this adder has been taken ahead of the block. This is C. And over here, this is R1. So now if you see output over here, it will be what? G1, G2 into R1, and over here C will be equal to what? C will be equal to G1, G2, R1 plus R2. So you can see G2 is missing over here. Rest all the things are same. So what you need to do, instead of giving R2 directly over here, you need to give it to a block whose gain is G2. So input of this block will be now R2. If this is the case, so this will be what? C equal to G2 R2. Now again you can see you are getting the same result. So that is why usually we remember that whenever your adder it goes ahead of a block, you need to basically do what? You need to multiply it with the gain of the block in the path of that adder. Okay, so that is what we are doing over here, you can see. So no need to remember anything. You can derive this concept well within few seconds. And in your objective type of paper, all the question of block diagram can be solved with the help of SFG. But still, sometimes it might be asked in your numeric kind of a question where there are options given and they will ask you what should be done if you want to shift your adder in front of a block. So you need to write what? You need to write simply that your input of the adder, it should pass through the gain of the block ahead which the adder is going, like in this case. Okay. So these are all the simple concepts that we have done. Okay. So concept, this was one of the concepts. So now we have few questions over here. So what we are going to do now, so we will solve all this question in your next class. Okay. So next class we are going to solve all this question. So today we will stop over here. Okay. So today we are going to stop over here. So in the next class we are going to finish this block diagram and SFG, and we will start with time response. Okay. Time response we are going to start. Okay. So then see you in the next session then. Bye everyone.